So then the next speaker is Bo Yang from Nanyang Technological University in Singapore, and he's going to talk about quantum geometry and topological events. Next.
Thank you. Hi, everyone. Let me first thank the organizer for this kind invitation. This is a wonderful program that has been prepared for the workshop. So today I'm going to talk about the quantum geometry in topological bands. So here, Landau levels, of course, are flat bands where the integer and fractional quantum Fourier effects are realized. And we also have the lattice analog of the Chern Insulators. What I'm trying to do here is to discuss with you about some of the fundamental relationships between Landau levels and the Chern bands. And of course, during the workshop, we have heard a lot about flat bands in lattice systems and array systems. So today I'm going to focus more on the physics in the Landau level. Okay, let me first thank my collaborators, one here from Conformal University. One here from Temple University, and also your job from Zhejiang University, China. And Jennifer Cano and Andy Millis from Behaviours Institute of the United States. And also my postdoc from Nanyang Technological University of Singapore, and Dr. Ji Guangyue. Okay, so let me first start with something I think most of you are familiar with. You know, for any quantum state, we can always undergo a local gauge transformation by attaching a phase that depends on the parameter of the system. But the cost of it is that the derivative is no longer gauge invariant. So we have to define a new type of derivative, the covariant derivative that is gauge invariant. Physically, it is a parallel transport of the physical state in the parameter space. And so with this covariant derivative, we can define this rank 2 tensor, which is not physical because it is gauge invariant. It can be separated into two parts. And I've heard about this in the workshop before. The anti-symmetric part is the Berry curvature, which is something we're familiar with. And the symmetric part is what we call the quantum metric, or Studi metric, that physically measures distance of two quantum states in the Hilbert space as defined here. And so this rank 2 tensor is what we call the quantum geometric tensor, which is important in condensed matter system because it impacts many of the experimental measurements, and we have heard many examples over the past few days. Because fundamentally, geometric tensor measures distances and angles, and in condensed matter system, we have different length scales competing with each other. For example, for this lattice systems, we always have a lattice constant A, fundamental lattice scale in the lattice. When we break the time reversal symmetry, we also introduce a new length scale from the Berry curvature, which is what we call the magnetic length, roughly equal to the 25 nanometers divided by the square root of Tesla. Right? So for a system with broken time reversal symmetry, they have broadly two types: the quantum Hall effect and the quantum Hall effect. And the insulator where quantum Hall effect is where the magnetic length is much larger than the lattice constant. So you can just ignore the underlying lattice details and treat it as a continuum system with only one length scale. So in some sense, it's simpler compared to the Chern insulator, where the effective Berry curvature can be up to like hundreds of Teslas. So here the magnetic length is comparable to the lattice constant. You can't ignore any one of them, and they compete with each other, and you have a much more interesting and much more complicated geometric effects in the Chern insulators. So far, from our understanding, the topological phases in these lattice analogs are really the analogs of the integer and fractional quantum Fourier effects in the Landau levels. And our understanding of how these states emerge from the lattice system heavily depends on our understanding of physics of Landau levels. In the earlier days, when we have these Chern lattices, like paradigm or Checker-board lattices, we have Chern bands with Chern number equals to 1. These bands are not that similar with Landau levels, even though they share a lot of common features. But more recently, with this development of moire lattices, where you have effective continuum model from the dominant moire potentials, here the Chern bands are much more similar to Landau levels. You can think of them as sort of like dressed Landau levels modulated by the moire potentials. So the physics in Landau level is even more important for these moire lattices. So I'm going to talk quite a bit about the quantum Fourier effect as a simple example, in the sense that it's quite complicated, but it's simple compared to the lattices because there's only one length scale. But I also keep in mind some and highlight some of the important ingredients that people who studying the lattice system will care about. Okay, so we all know the quantum Hall effect is realized by applying a strong magnetic field perpendicular to the electron gas system. I don't need to talk too much about it. So the single particle Hamiltonian can be solved analytically to form these flat bands called the Landau levels. Right? The Landau levels are dispersionless because there's only one length scale, and also have uniform Berry curvature, uniform quantum geometry tensor. So it's a very simple continuous version of flat band, and the number of states in the Landau level is given by the area, as you can see over there, the area of the sample divided by the area of a single magnetic flux. So that's analogous to the number of unit cells in the system. Okay. So the surprising experimental measurement in 1979 is that when you measure the core resistance as a function of the magnetic field, you see these plateaus forming corresponding to integer number of these flat bands that are completely filled. We know it has a topological origin. When you completely fill these flat bands, the ground state has a gap, and also the gap is larger than the temperature or the disorder in the system. And the reason why you can see these plateaux is also because of the important physics of Anderson localization. So when you have fully filled band and add more charge carriers to the system, in 2D there are impurities that will always localize these additional charge carriers. So that's why in a transport measurement, you can see these plateaus. Without disorder, the topological phases will not be affected, but the transport measurement is not able to help you to distinguish between topological phases and non-topological phases. You'll just be seeing a straight line with a gradient giving you the information of the charge carrier density in the system. Here, I also want to advertise our recent work here, showing that in a Chern band, or in a Landau level, where you introduce a new length scale of an electrostatic superlattice, depending on the comparison between this length scale and magnetic length, this superlattice can sometimes completely suppress Anderson localization in the topological band, and sometimes it can enhance it. This has critical consequences because it affects the width of this plateau. The width of the plateau is an effective measurement of the amount of localization or disorder in the system. And what is important is that in the lattice system, of course, we have a lot of length scales. So the localization effect, calculation of the electrons in the Chern band in the lattice is also something that is very interesting to look into. Okay, so this is the integer quantum Hall effect. The fractional quantum Hall effect is when you go to even larger magnetic field, cleaner samples and lower temperature, you realize that these plateaus can also form when a flat band is partially filled, indicating the ground state also has a gap, and this gap has to come from the interaction. So this is a typical example of topological orders emerging from strong Coulomb interaction between the electrons, where in 2D you have these interesting collected excitations that are anyons or non-anyons, which can store and process quantum information in a robust way because they are topologically protected. So it's also kind of useful. So normally people think of fractional quantum Hall effect, integer quantum Hall effect as separately because integer quantum Hall is single particle physics, fractional quantum Hall is many body physics. But here I'm going to introduce a rather universal common perspective in understanding quantum Hall effect in a common framework. This could especially be useful to people who are not very familiar with quantum Hall effect. Because quantum Hall effect is a very good example where universal topological properties emerge from the algebra of the Hilbert space, where if you truncate the Hilbert space, you have, in a systematic way, there is emergence of new elementary degrees of freedom. The key thing here is the Hilbert space truncation, which is not kind of exotic because when you go from 3D to 2D, you're already truncating the Hilbert space, right? Because quantum Hall effect can only occur in even dimensions. But in a 2D Hilbert space, if you apply a strong magnetic field, you are again truncating the Hilbert space into a single Landau level because all higher Landau levels are at very high energy, at low temperature, they're not accessible. And in this truncated Hilbert space, in principle, you're not dealing with electrons anymore. You are dealing with some kind of quasi particles carrying the same charge and spin as the electrons, but they're no longer point particles. You can't confine everything in a single level to a point because the quantum fluctuation will bring it to higher Landau levels. Same thing coming from the kinetic energy. So these fat fermions are basically, for all physical purposes, the elementary particles for low energy excitations for the integer quantum Hall effect. These are the poles for the integer quantum Hall. In this truncated Hilbert space, physically spanned by the ground state, which is a fully filled band, treated as a vacuum, and with Hall excitations, which can also be interpreted as edge excitations due to the bulk edge correspondence. So here is an example where you do truncation with kinetic energy of the system. But if you think of truncation as an overall theme, you can also try to truncate in other ways. For example, of course, using interactions. Here is a family of very special interactions between electrons. We don't have to know the details, but what they do is they define a low energy Hilbert space, in this case, exact zero energy Hilbert space, within a single Landau level. Meaning that at low temperature with the interaction, only a subspace in a single Landau level that is physically accessible. And in this subspace, for all physical purposes, the elementary particles are no longer electrons or quasi-particles. They are now anyons that can carry a fractional charge and fractional, even non-abelian statistics. So the overall message is that the interaction here is a tool for you to further truncate the Hilbert space from a single Landau level to a subspace. And in this subspace, every one of them corresponds to a particular type of anion and also corresponds to a particular type of fractional quantum for topological phase. Okay, and they also have these nice structures. Every Hilbert space is also very special. I call them the conformal Hilbert spaces because they do have emergent conformal symmetry in 2D. I'm going to talk just a little bit about it. So the special feature of these Hilbert spaces is that every one of them has a highest density state corresponding to the ground state of a particular phase. And the entanglement properties of this ground state actually contains all information of all other states in the same Hilbert space. And these are what we call the anion particle excitations or the edge excitations if you put the quantum Hall fluid on an open boundary system. So this is the fundamental reason why there is bulk edge correspondence or a holographic description of these conformal Hilbert spaces, where all these states, other states can be generated by applying these conformal algebra, conformal generators to the highest density states. So it's highly structured algebraically, and this is actually important for the topological properties as well as the physical experimental measurements of these topological phases. It is universal for integer or fractional quantum Hall effect. It should also be universal for all those topological phases in the lattice system as well. Okay. So quick summary is coming from 3D, we truncate the Hilbert space to 2D. And in kinetic energy, truncates the Hilbert space into a single Landau level where we have integer quantum Hall of particles. Interaction truncates further to a smaller Hilbert space, a conformal Hilbert space, where anions play the most important role, and they can have very interesting properties. Okay? And also, there is this very interesting hierarchical structure of different conformal Hilbert spaces coming from different topological phases. But every one of them can be solved as a topological physical space or a flat band. A single Landau level is a special case of a single party flat bands. But all these conformal Hilbert spaces are many-body flat bands with a special Hamiltonian. They do all have zero energy, really just a flat band. If you perturb these Hamiltonian physically, then of course the band will have a small bandwidth, but as long as the interaction of the perturbation is small, the topological feature will not change. Every one of these conformal Hilbert spaces will have elementary particles like anions or particles with very special properties. More interestingly, these particles are not featureless. They can even have internal structure if you view them properly, for example, from a larger Hilbert space. Right? So the example is that if you look at the Laughlin 1/3 conformal Hilbert space, if you just look at everything within this conformal Hilbert space, then you'll see elementary particle is Laughlin particles. And in this Hilbert space, Laughlin particles are featureless, just like a fat fermion. Just like if you look at water at low energy, what do you see? Just water molecules. You can't really see anything inside the water molecules. But if you look at the same Laughlin particle in a larger conformal Hilbert space, not working, say in the Gaffney or moire conformal Hilbert space, then you see the Laughlin particle is just like a hydrogen molecule, which is a pair of smaller particles. They can interact and they can be attractive or repulsive depending on the interaction. Just like if you look at water at high energy, you realize water molecules are made of hydrogen and oxygen atoms. So that's also very physically can be easily analyzed using this conformal Hilbert space structure as well. Okay, and also if you perturb the system, these anions are no longer like ideal gas. They can even start to interact with each other, which is quite common. And these elementary particles, in some sense, can also be force-mediating particles, mediating interaction between other type of anions as well. Okay. More importantly, these conformal Hilbert spaces can be parametrized by geometry, for example, a metric, or it can be parametrized by central mass momentum describing the spatial modulation. Okay. This is fundamentally coming from the fact that the topological physics here doesn't really rely on any spatial symmetry like rotational symmetry or translational symmetry. It's not easy to sort of engineer these kind of things in a quantum Four system, but in a lattice system, it's actually very natural for these conformal Hilbert spaces to have different geometric aspects, simply because you have many more land scales playing around with each other, and they can be naturally realized. So that's also something that one can try to study in the lattice system as well. So here's a summary of the sort of the application of this conformal Hilbert space perspective. In the top left side, what we show is that indeed Laughlin quadripoles have internal structures like a pair of molecules, and they can even fractionalize and become repulsive between the two particles if you go to the transition between the normal fractional quantum Hall phase and the nematic fractional quantum Hall phase. The nematic fractional quantum Hall phase has been seen in experiment. So in the vicinity, we're predicting this kind of interesting dynamics of the Laughlin quadripoles. On the top right side, we show that every conformal Hilbert space can be parameterized by a metrical shape, and this shape can undergo quantum fluctuation, leading to neutral excitations and like graviton-like neutral excitations with a chirality. This chiral graviton was also recently measured with unit Raman scattering in this particular paper. Of course, there are a lot of works on this graviton-like excitations. And for example, the first one who proposed this multiple graviton mode is actually Zun sitting here from the effective theory perspective. But it's also very natural to see this from a more microscopic point of view, using especially the conformal Hilbert space structure. So here on the top bottom left side, we can also show that conformal Hilbert space is special because within this conformal Hilbert space, anyons, bosons, and fermions can be related by rigorously related by non-local unitary transformation, implying that we can actually bosonize anyons in a 2D system within a conformal Hilbert space. Right. Lastly, on this side, we show that of course anyons are not point particles. They occupy a finite area, means that they also have a shape, and this shape can be deformed in a conformal Hilbert space or in the low energy manifolding experiment. This deformation will be important if we're braiding the two particles around each other, because there will always be impurities and some other disorder in the system deforming the shape, leading to corrections to the Berry curvature when you braid them, and affecting the spin statistics theorem as well. And this is something we also try to capture in this particular paper. Okay. So it's just a summary of a snapshot, a very small part of interesting physics in fractional quantum Fourier effect. And of course, the long-term goal in the lattice system is how can we also realize interesting things that you see in the fractional quantum Fourier in the lattice system. And the hope is that because of the rich tuning knobs in the lattice system and different land scales, some of the things that is difficult to see in quantum Four may be easier to see in a lattice system as well. So that's also something to think about. Right? So I'm going to also talk a bit about pseudo-potentials. I don't know if I have time. Okay, so pseudo-potential is a physical way of realizing conformal Hilbert spaces. Also, it is a useful analytical tool in analyzing both the phases in a continuum system or in a lattice system. So the reason why we use a pseudo-potential is because the Hamiltonian interacting Hamiltonian is very difficult to solve. So we take a step back and say, if we can't solve it, can we try to solve some special models at least partially? So that's the idea, right? So the way to do that, indeed we can. For example, if we take a special case of the effective interaction V of Q here in this particular form of the Bragg polynomial, then we can solve the ground state and quadrupole states analytically. They are the Laughlin states, defining the Laughlin conformal Hilbert space analytically. Because physically, this happens to be just a set of projection operator, projecting into any pair of electrons where the relative angular moment is equal to 1. So you can rewrite the Hamiltonian into a set of projection operators. Okay, so the useful thing is that if we have nice pseudo-potential formalism, that's like a tight binding model for the fractional quantum Four, right? It's highly unrealistic, it is artificial, but it is useful, and it can be solved in some sense, right? And it's useful because we can just look at a two-body spectrum that can tell us a lot about what happens to many-body spectrum. There are a lot of caveats in here, of course, but it's still quite useful too. Right, so I have to hurry a little bit. So it also formed the complete basis. I think I'll just skip this. As long as you get the general idea, they are just projections to a cluster of particles with a particular angular momentum sector. These are what we call pseudo-potentials. You can even write them in the space as a projection operator for member lattice. But I guess I'll just skip. Okay, So next I'm going to talk about the geometry of the Landau levels, because geometry is playing a very important part in understanding what happens in a Chern band, right? The question is that why are they successful and are there any limitations? We have to take a little bit of care to understand when geometry works, because geometry is just a long wavelength part of the wave function. It is not everything. Okay. But the geometry of Landau levels are very simple in some sense. It's uniform everywhere, especially for the Berry curvature. It's uniform and same everywhere and for every Landau level, because it just gives you the magnetic field, which is unique. However, the quantum metric is much less trivial. The quantum metric is uniform, but it is different for different Landau level. It's given by this 1 + 2n, where n is Landau level index. Physically, it dictates the single particle wave function has a z star that has the highest power equals to n if it's living in the nth Landau level. But this n just indicates the orbitals in a single Landau. Okay, so this feature actually tells us different Landau levels are qualitatively different. Okay, the easiest way to see this is to look at an interaction, which is at the lower left corner. That the shortest possible interaction in the real space is a contact interaction, right? This contact interaction projecting into Landau levels just gives you a small set of pseudo-potentials projecting into different angular momentum sector. But in the lowest Landau level, the projected interaction is just V0. So it gives you energy punishment when a pair of particles have angular momentum equals to 0. But in the first Landau level, it's equal to V0 plus V2. In a higher Landau level, it's V0 plus V2 plus V4, etc., etc., etc. If you're talking about fermionic systems, in the lowest Landau level, it corresponds to just V1. In the next Landau level, it's V1 plus V3. In the next Landau level, it's V1 plus V3 plus V5. What that means is that if you want to realize exactly the law of 1/2 or 1/3, you can only do that in the lowest Landau level. It's not possible to realize the exact zero energy states in higher Landau levels. You can still realize the topological phase, but it's more difficult in terms of the property is less robust, right? It also implies from a theoretical point of view, you can't relate different Landau levels with local unitary transformations. They are qualitatively different, even though the Chern numbers are the same everywhere. Right? It also tells us, in some sense, yes, trace is useful because we do want our Chern band to have a smaller trace if you want to realize these abelian plane states or Laughlin state. Otherwise, wave functions, the effective interaction is always going to be more long-ranged, making the realization of these states much more difficult. Okay. Another interesting consequence is that think about the case when the interaction is actually much larger than the band gap for short-range interaction. One can show analytically, right? Normally, a strong interaction will mix bands, but if the filling factor is low enough, for example, if I have contact interaction with just a delta function, if my filling factor is smaller than 1/2, no matter how strong the interaction is, there's no way for you to mix the bands. All particles can just happily stay in the lowest Landau level, avoiding each other, and they won't be punished. This can be generalized to other systems as well, other interactions as well. Only when the density or filling factor exceeds certain critical density, then you are forced to mix different bands, lowest 2 bands, for example. If you exceed another critical filling factor, you have to mix 3 bands, etc. Okay, so this is actually interesting observation from the pseudo-potential perspective. The reason why I mention this is because there is this interesting paper showing that in a lattice system, when you have a nearest neighbor interaction, short-range interaction, no matter how strong that interaction is compared to the band, you can never destroy the Laughlin phase at 1/3. So it's just a numerical evidence with no, not an intuitive understanding, but the physics is actually explained here, right? Because the filling factor is low, and a short-range interaction is not able to mix Landau levels or different bands, no matter how strong that is. So it's a good way of understanding some lattice systems from our understanding of the simple Landau levels. Okay? And also, mixing of Landau levels are not common in quantum Hall system, but they're very common in lattice system. In lattice system, the trace condition is never the uniform or integer, right? So that means actually you can look at cases where the trace is not equal to a constant number. But the key thing here is that this is just a little bit of a caveat that if you just look at the geometric aspect, it doesn't tell you the whole story. What I'm showing you here is many different bands of mixing different Landau levels. They all have the same quantum geometric tensor, meaning the trace is always the same, and it's the same type of interaction, but So physics is actually very different, as you can see from the ground state overlap with afterwards. So the key message here is that you need to be a bit careful as well. It depends on the filling factor and also the interaction. The quantum geometry doesn't tell you everything. Right? So here is an analytical calculation to show that if you look at pseudo-potential from an interaction of the Gaussian type, then only for short range, it's only for the leading few order, 8 to the power 4, 8 to the power 6, it only depends on the trace. If you go to higher orders, then there are corrections that are not dependent on the trace and on the geometry anymore. So we'll always need to be careful a little bit about the interaction range. You can't just always only think about as a quantum geometry. Okay, all right. So, but the thing is that, of course, lowest Landau level is quite special. If you have a trace condition that agrees with lowest Landau level, there's nothing you can mix, right? Because that already saturates the bond. So I'm going to use this example to show that this is also kind of simple because in twisted biography, you can have a band that looks like the lowest Landau level. And the reason is that we can go to the chiral limit. So I'm not going to, I think I don't have to talk too much about it, right? So we have a coupling between two bands. If one of the coupling constant is 0, then it's a nice model that gives you the exact flat band with the Chern number equals to 1. Okay, and the reason why it's the exact flat band is because the Hamiltonian is chiral, so you can construct wave functions that are just a polynomial of z, but it is only a valid wave function when the angle of rotation, twisting angle is of certain values. Otherwise, it's not a valid wave function, it diverges somewhere. So it's a good way of defining the magic angles when it's a flat band first. Okay, so what is, yes, yes, okay, I'll be very fast. Okay, so the key message is here that we realize that we can write down the wave function as a modulated lowest Landau level wave function. The key thing about this band is even though the Barry curvature is non-uniform in k-space, like in the lab coordinates, but if you look at the ratio of Barry curvature with its trace of the metric or determinant of the metric, it's a constant. So if you do a measurement of physical density of Barry curvature in the Hilbert space, it is uniform like a lowest Landau level. So that's why the physics is very simple. Right? So I'm going to be fast. So our goal is to try to capture this using quantum Hall physics, using pseudo-potentials. I'm going to skip these technical details. The main idea is that we can generalize a pseudo-potential to cases where I break translational symmetry. Okay, so what we see here is that we can capture the physics of chiral limit of CTBG with the fraction quantum Hall system with a uniform Barry curvature. So price we pay is that if we have a uniform Barry curvature, our interaction cannot be uniform anymore. I have to have a central mass part of the pseudo-potential. That's a generalization saying that I can generalize the pseudo-potentials to be breaking rotational symmetry and translational symmetry, but they still are very well behaved. In a sense, this is just a numerical test to show that they're really the same. Okay, in a sense that they can define an exact zero energy subspace, which is a conformal Hilbert space I mentioned before. But these conformal Hilbert spaces now has a non-trivial central mass dependence, which has some consequences, for example, about Lufrig suggestions as well, which I'm not going into details here. So an example here to show that the Lattice system is a very natural way of realizing rich conformal Hilbert space or topological systems with geometric enrichment in some sense. Okay. But does that mean the quantum CTBG and RL are the same? So they are actually not the same. That's also one thing that one needs to care for, even though both of them satisfy the aggregate band situation. The range of interaction is something I mentioned before, right? You have to be careful about that. The next thing is because of variation Barry curvature, there's a lack of particle symmetry. An interesting example is shown here. I'm almost done. So if you look at a single electron in a flat band, it's pretty dispersionless. But if you look at a single hole in the band, it's not dispersionless with interaction because of this Barry curvature. What is interesting here is that for a large family, almost all the interaction you consider, the whole energy traces the Barry curvature very nicely. This is not something obvious. For short range interaction in Q space, it is obvious, we can show analytically, but for long range, that's not true. But because maybe of the form factor decay, this is indeed the case. We can use the whole energy to track the curvature or the quantum geometric tensor in the system, in the CTBG. It's not as good in the Lattice system, as you can see on the left, on the right. They are close, but they're not that close. So that's one thing. But if you look at the interactions of many-body system, here is also an example to show that with the same interaction in half-filling, you still have very different spectra in the lowest Landau level and in CTBG. So when you say they're the same because the quantum geometry is the same, you also need to be a little bit careful. Okay, I'm going to skip this and I'll go right to the summary. So the vorticity part is if you go beyond lowest Landau level, there's also a set of tools to try to mimic lattice system with Landau level, but there are also caveats in here, which I think we can discuss later if you're interested. So here's the summary. I just want to show also we also recently found that for any lattice system, we can actually fit the quantum geometric tensor of any lattice system with Landau level by locally mixing Landau levels. And even with just the 4 or 5 Landau level, we can reproduce a quantum geometric tensor almost exactly 10 to the power -10. This is actually very non-trivial because what we're doing here is to solve a system of equations where number of equations is much larger than number of parameters, number of variables. It's overly constrained. Normally there's no solution, but there's always going to be a solution, showing that there's some universal feature for Landau level mixing for these lattice systems. And that's a summary. I'll do. I think I don't have time. I'm happy to answer any questions. Thank you.
Okay, any questions?
I have 2 short questions.
So yeah.
First, you showed that the injection and filling driven Landau levels will not play wonders if it's not destroyed, no matter how strong the interaction.
Yes, exactly.
Is that for only the nearest neighbor or like all sorts of short interactions?
Yeah. So the example I showed here is in a continuum system. So it's just a very short range interaction in the real space. Okay. So I think what you're talking about is a lattice system. So indeed, it only works for short range interaction, like nearest neighbor interaction. If you have longer range interactions, the Landau level mixing so the band mixing by this interaction effect will be very strong, and you're going to destroy the one surface, unless you go to even lower filling. So if you go to next nearest neighbor interaction, but your filling is like 1/5, etc., then there's a high possibility. Also, those states are very robust when you go to very large interaction.
And also, you showed that the TBG is an ideal band.
Yes, yeah.
And I was curious if there is other example of ideal band other than TBG.
Other than TBG, I think there are. I can't name the exact samples. For example, in those TMB system, you can also engineer the system to make them ideal, at least almost ideal. What I know is that for many moire systems, if you look at the trace condition, when the Chern number is equal to 1, like the one shown yesterday by Joe Young, the case when you have multiple Chern bands, so the trace average is 1.0 something, so it's very, very close to 1. So it can be almost ideal. And chiral TBG is also an approximation. The realistic twisted value graphing is not in the chiral limit, and the trace is not equal to 1, but very close.
Okay, yeah, any questions on the Dresden side?
Yeah. Thanks for the talk. Do these results for the similarities between the fractional quantum Hall effect and the chiral limit in TBGs generalize to other chiral situations in multi-layer graphene systems or for other magic angles?
Yes, so if for the lowest Landau level, it's actually quite universal. For the lowest Landau level, if you want to saturate the trace, there's only one way, right? You can't mix different Landau levels. So as long as your trace is very small, like very close to 1, then at least numerically what we can see with Coulomb interaction, the dynamics are very similar with low filling factors, like filling factor 1/3, etc. But even with filling factor 1/2, then you have to be a little bit careful already. And for filling factor that is larger than 1/2, that is the particle conjugate of 1/3. Then for 2/3, the physics will be very different from lowest Landau level and those band systems because of lack of particle symmetry. So if you're talking about higher Landau level like things, I think yesterday was this talk about the MOT2 system when they can have a moire band with trace very close to 3. Then numerics show that, it also with Coulomb interaction, it looks very much like the first Landau level physics. One needs to be careful. Sometimes you have to check, but it can happen that the two systems are very close. Hope that answers your question.
So I'm a bit confused about your result when it comes to the Landau level mixing. First, the paper by Titus and co-workers, they work in a Chern band, so they have opposite Chern numbers for the 2 bands. Right. The setup that you have shown is, the Landau levels where you all have the same Chern. So could you comment on this one? Maybe the second question is, imagine I have only 2 Landau levels, the lowest one and the second Landau level. I know that I can hook up a short range interaction to get the Jane state exactly.
Yes.
Now I'm a
yes,
bit
yeah.
confused about why you would get the Laughlin as the exact ground state, and not among like a a whole lot of quasi-Hall excitation.
Yeah, so actually, no, you can't get Jane state if the fitting factor is smaller than 1/2. You can get Jane state if the fitting factor is larger than 1/2. This is the bosonic version, by the way. So if you go to fermionic version, it's from between 1/3 and 2/5. So we can get exact Jane state when the fitting factor is large enough, as long as it's below 2/5 or 3 to 2/2. That's exactly what we are saying when you mix two Landau levels. So there's no contradiction here. The reason why only see Laughlin state is when the fitting factor is below the Jane fitting. Then you only have low. Then if you're talking about the comparison between these two, there is a crucial difference, of course. Here, each Landau level have Chern number equals to 1. But in this particular paper, they look at the case when Chern number is 1 or -1. But I think the physics is the same. The question is that what happens if you have interaction in one band, and this interaction is much larger than the band gap? Okay. The question is, can you fit all the electrons in a single band, and somehow you tune up the interaction? The electrons will not feel it. Because they are further away from each other, they don't feel the divergence of the interaction. That's what is happening in the Landau level case. And I think it doesn't really matter those higher Landau levels how they behave. For example, I can engineer another Landau level with opposite magnetic field that has higher energy with a Chern number equals to -1. But as long as my lower Landau level has fitting factor smaller than 1/2, no matter how large my interaction is, I don't have to care about all the other Landau levels, all the other Chern bands, basically. So that's why I say the physics is the same here. I hope that answers your question.
Okay, we can discuss more.
Okay, sure, yeah.
Any other question?
Yeah.
Well, if not, then let's thank the speaker again.
Thank you.